Okay, good afternoon, everybody. Today we have the class for second BSc, that means fourth semester abstract algebra. So, so topic is mathematics, mathematics, permutation groups, permutation groups. So we have earlier discussed different kinds of topics on abstract algebra, beginning with the groups definition, groups, subgroups, cyclic subgroups, normal subgroups, later the cosets, later then later we are now having the topic permutation groups. For this purpose, now we go to the photos. On photos we have this topic, that is on permutation groups. We are going to discuss the orbit of and the cycle of the permutation f is equal to 1 2 3 4 5 6 2 1 3 5 6 4. Here we are given s is equal to 1 2 3 4 5 6. So what we have to take in is the elements, the different elements taken on permutation. Those are 1 2 3 4 5 6. So f is equal to, we are having 1 2 3 4 5 6 2 1 3 5 6 4. So we know 1 belongs to s. Now find f of 1. That is the place, second row, element in second row against 1. That is 2. Look, square of 1. F of 1. F of 1 is 2. F of 2 is equal to 1. F square of 1 is equal to 1 we got. The element we have in bracket is equal to the same element. So here we have to stop and we have to write the orbit. Then we can have orbit 1 f of 1, cycles 1 2 permutation. Now we go to second element, 2 belongs to s. F of 2 is equal to 1. F square of 2 is equal to f of 2 is equal to, f of 2 is 1, f of 1 is equal to 2. F square of 2 is equal to the same element we got here. F square of 2 is equal to 2. The element in bracket is 2 is equal to 2. Same element we got. That's why orbit of 2 is 2 comma f of 2. So here orbit is equal to 2 comma 1. Cycle is 1 2 comma 1 in private bracket, right? Now we go to second page. For second page purpose, now we are having this one. 3 belongs to s. F of 3 is equal to 3. The element in second row against 3 in first row is 3. Orbit of 3 is, so directly with one step we got f of 3 is equal to 3. Same element we got in bracket is equal to the same element. So orbit is 3. Cycle is 3. Next we go to another element. 4 belongs to yes. 4 belongs to yes. F of 4 is equal to 5. F square of 4. F of 4 is equal to f of 4 is 5. Write down f of 5 is equal to 6. So now we go to f cube of 4 is equal to f half f square of 4. F square of 4 is 6. Write down f of 6 is equal to 4. F cube of 4 is equal to 4. F cube of 6 is equal to 4. Now we got f cube of 4 is equal to 4. Same element we got on left and right sides. Then we get orbit of 4 is 4 f of 4 f square of 4. 4, 5, 6. Cycle is 4, 5, 6. Now we go to another element. 5 belongs to S. F of 5 is 6. F square of 5 is equal to f of 5. F of 5 is 6. F of 6 is equal to 4. So now we go to another element, another step. F cube of 5 is equal to f of f cube of f square of 5 is equal to f of 4. F of 4 is 5. F cube of 5 is equal to 5. So here we got f cube of 5 is equal to 5. The same elements on left and right sides. 5, 5 values we got. So orbit of 5 is 5 f of 5 f square of 5 f cube of 5. That is 5, 6, 4. Okay. So now we go to another page. Now 6 for 6 purpose, if you find f of 6 is equal to 4, f square of 6 is equal to f of 6. F of 6 is given 4, f of 4 is 5. So f cube of 6 is equal to 6. Directly we got the same element on left and right side. Orbit of 6 is 6, f of 6, f square of 6. So what we got? What we got? 2, 5, 6, 4, 5, 6. Cycle is 6, 4, 5. This is the solution we have to find for this question. Now we are having homework purpose leave those things, and now we got here cycles of permutation. So cycles how we can find. Now we are given a permutation we assume. Then we write then we write cycles. Cycles means here we are given this type of permutation is called cycle. Here we are given f s is equal to a1 to ak. Now f is given a1 to an and a2 to a2 to an. So in this definition, this type of permutation S is called cycles. Permutation of length k under degree n, if f is printed as f is equal to a1, a2, a3, so on, ak is known as cycle. So this is the question we have to find out. Simply now we consider a an example. So that example can be simply, now we suppose we are given a permutation 1, 2, 3, 4, 5, 6. In this permutation, we have we have supposed 2, 3, 3, 4, 5, 2. Now 2, 3, 3, 4, 4, 1, 4, 2. This type of formation we supposed. Remaining things are same. Then also we have connected, we are given a connection. That connection is found by first element, second element. In first row, second element and another element. In first row, that another element and the first beginning element. Like that we are given. So then cycle can be 2 3 4, 2 3 4. But this one is a cycle. In the same manner, we get another cycle. And after second cycle, we may get third cycle, fourth cycle, whatever number of cycles we may get. All those cycles can form a permutation. So here we consider transposition. Cycles we have observed. Cycles we have observed. Later on, now we go to observe transpositions. How a transposition can be defined? A cycle of length 2 is transposition. So in transposition, only two elements can form a transposition. That's why a cycle length of 2 is known as transposition. Now we go to another page. Here a cycle of length 2 is called transposition we are given. So here example also is given. F is given A1 to AK and A2 to AK like that. Here F is A1 A2 A1 A2. Its length is 2. And here you see another S is equal to 1, 2, 3, 4, 5, and a permutation is F is equal to 1, 2, 3, 4, 5, 1, 3, 2, 4, 5. Here, here you see cycle is only 2, 3, 3, 2. So beginning ending same. That cycle is taken as 2, 3. So itself of length 2. So it is a permutation. So remaining 1, 1, 4, 4, 5, 5 will be same. They cannot form a transposition. Like that we can like that we can define a transposition. We can find a transposition. So after those things, now here we are getting odd and even permutations. Odd and even permutations are we can find out the number of transpositions is even. The number of transpositions in a permutation is even. That permutation is even permutation. The number of odd, the number of transpositions in a permutation is and that is odd permutation. So like that we can define odd and even permutations. Now here we are given an example also. So here we are given some conditions. What conditions? Product of two even permutation is given. Product of two odd permutation is always odd permutation. And the product of one even and odd permutation is even permutation. Like that. Uh, and identity permutation is always even permutation. Like that we can find out different kinds of permutations. So now, so this is the topic I would like to discuss. So like that, here we have to find with an example uh, even permutation and odd permutation. Now suppose we are given 1 2 1 2 2 3 3 4 4 5 5 4 2 5 5 6 6 7 7. Here we got a cycle. That cycle is 1 2 4 1 2 3 4. Here we have to find out whether this permutation is odd permutation, even permutation. So for that purpose, how we can find out, now write down 1 2 a transformation, 1 3 a transformation, 1 4 a transformation. So we got 1 2 1 3 1 4. How many transformations we got here? Three transformations. So this permutation is odd permutation. So we got odd number of permutations, transformations. So given permutation is odd permutation. If you get even number of cycles, even number of transpositions, then that permutation is even permutation. Like that, we can find out odd permutation, even permutation. So this is the position we have to discuss. And here, product of two even permutations is even permutation. And if you are given the product of two odd permutations, so itself can be odd permutation. And the product of one even one odd permutations is even permutation. And is identity permutation is even permutation. Like that, we are having different kinds of permutations. So now we go to beginning of this question.